our speaker, okay? So just so you know. All right.
Okay, then let's get started. Yeah, so I'll bring you through just my educational and work background, and I'll talk exactly about what an engineering PhD is, because I think it's kind of confusing. I certainly didn't know about it when I was in high school. I didn't find out about it until my junior year of college, and I wish I knew sooner just to prepare a little bit better and maybe adjust some things. And then I'll talk about what are cyber physical systems and what is exactly power systems research. And then a couple different projects I'm working on in traditional power systems and electrified aircraft and urban air mobility with vertical lift and drones. Okay, so I'm right now doing my PhD at RPI in electrical engineering. My main research areas are in power system dynamics, cyber physical system modeling, and system identification. And I'll explain that in a little bit. I got my master's of engineering in 2019, along with my bachelor's in electrical engineering, both in the same semester. I can explain that too. And then I finished Colony in 2015. So everything that you guys are going through right now, well, not remote, I was in person, but all the same courses I took as you guys. So I have, yeah, so the applications are pretty much the same. And then I'll go through my work experience a little bit quick. Okay, so why did I get interested in power systems engineering in the first place? So power systems are really cool. It's a really amazing engineering feat that impacts literally every part of our life. Like, society wouldn't exist today without it. Like, when you lose power, like, your life is like significantly diminished, not in just terms of like entertaining yourself, but you can't cook dinner, you can't wash your clothes, the street lights are off, and life is just crazy. So right now, we're currently undergoing a lot of changes with climate change and trying to make our grid more green. We're looking into electrifying other areas, such as transportation too. So we have all these new engineering developments, and I specifically picked a research career path because of the flexibility and creativity it offers. So when I was in high school, I decided after taking the digital electronics course from Project Lead the Way that I was going to be an electrical engineer. I loved it. I thought it was super cool that you could put all these little components into a breadboard and just make something light up. And I also was going through high school around the time that we started talking about transforming the grid, all this green energy. And I know right now, like, pandemic safety and stuff is having a hot moment. But back then, renewable energy and stuff was really where the conversation of future careers was at. So I took calculus and AP physics and all those types of courses to prepare. And then when I went to RPI, I specifically, when I was looking for a college, I wanted to go to a polytechnic school just because my personality fit better in with the kinds of kids that everybody there is an engineering major. It really doesn't matter. You go where you're happy. I'm not gonna lie, I picked my school so I could run cross country and track. And that was just something I did because I knew that was going to make me happy. And I know a lot of the success I had in undergrad and my master's degree was specifically tied to just being able to be around a lot of people that made me happy and gave me some sense of like foundation and support while I was there. So I did a combined master's and bachelor's program. So I took grad courses at the same time as my bachelor's degree. So every engineering course program is your first 2 years, you take the basics in math and science. So if you take all these AP courses, I know Colony, I think now cross-registers with Hudson Valley too. So all these community college courses can be applied to your bachelor's degree, and you can like skip out on a year. That's what I did. So I could finish both degrees in 4. And then after that, every electrical engineer takes a course in every fundamental area. So digital and analog circuits, electronics, microelectronics, machines and power systems, fields and waves and signal processing and control systems. And then you take extra courses in whatever area interests you most. For me, that was in power systems. So that would be like power electronics, electricity markets, large scale power generation and control, renewables modeling and stuff like that. And then while I was an undergrad too, I also did 3 semesters of research in the lab that I'm in now, which really helped me solidify the decision to do a PhD, especially in the lab that I'm in. Oh, Reload. Okay, let's see. Let's try this again. One second. I don't know why that's not loading. All right, I'll just show this slide down here. Can everybody still see it? Yes. Okay. So while I was an undergrad, when you're an engineer, we actually luck out a lot. We can be interns over the summer. A lot of companies do it, and they pay well. So if that's something that you want to consider for your finances, we make like way more than minimum wage. So it's like a really good deal. So I worked power systems deregulated. So what that means is not the same company in the United States owns the generation, the transmission, and the distribution. So you might get power from National Grid, and they control all of those lines that are around your neighborhood, but a different company controls the big transmission lines that you see, and a different company is the one that operates the power plants. So there's these companies that we've developed out of this deregulation called independent system operators. They oversee all of the bulk transmission in the grid. So I spent 2 summers working at the independent system operator of New England. So they handle all the planning, markets, and operations for New England's grid. And I worked in day ahead forecasting, which helps us plan how much power we need for tomorrow and when we need it. Specifically, I worked on how everybody's putting solar panels on their homes and businesses. You'll see them around town, and this reduces the amount of load that the system operator sees. So that little figure on the right, which is why I wanted to show it, is something we call the duck curve. So during the day, everybody's solar panels on their houses are taking in power, and the system operator doesn't see as much because all that load is already served to your house. So as the sun sets, now all of this demand is now coming onto the grid. So we have to be able to plan that because plants just can't work instantaneously. We have to plan in advance to know to ramp up how much fuel we're going to use. So this is a big problem. And the way we do this, we need to figure out how much solar power is going to be generated by these houses every day. And the way we do this is through machine learning. So there's applications from other really popular areas of computer science and engineering right now that have a direct application to power systems. I also spent a summer between my master's and PhD working at the Electric Reliability Council of Texas, or ERCOT. It serves the same role as an independent system operator, except Texas is its own grid. So we have 3 grids in the US. We have our Western Interconnect, our Eastern, and then Texas. So they can do their own thing if they want. And then we just couldn't build lines over the Rocky Mountains. So that's why we have 2 grids. And then the third is just because Texas is weird. So I worked in dynamic studies, working on how we're going to commit these wind plants to the Texas Panhandle. So not everybody lives in the Panhandle of Texas. So there's all these new complicated intricacies of trying to get power from a really remote area to big cities that are on the eastern and central part of the country, or of the state. So that was a big study that we did there. And now I am working as a research assistant in the LSAT lab at RPI. We're a simulation and modeling focused group that works primarily with power systems and electrified transportation. I work mostly with development, modeling, and simulation of electric aircraft power systems, both with fixed wing and vertical lift, so like drones. And then I also do system identification and estimation of power system controls. So what that means is, how do we know that the models that we have for really old plants in our power system are still accurate for what we still have, what we're operating with today? Now it wants to load. So before I get into everything, what exactly is a PhD in engineering? So it's a little bit different in terms of a role from other traditional PhDs that you might think of like from physics or biology or something. It's essentially just training that prepares you for a research-based position. Basically nobody works in academia, since those roles are few and far between. So a lot of us go into industry or in a national laboratory The group I worked with at ERCOT with all of those wind turbines is actually one of those groups that works in a specialized role and has a lot of PhDs. So that's some sort of job that you would have with a PhD. And engineering PhDs are much shorter. They take 3 to 4 years compared to physical and social sciences that are like on the scale of like 6 to 8. And that's mostly just due to the nature of our research. The results that I can get from my research, I can get pretty much instantaneously. I can get them like, I'll run a simulation and there's my results, versus physical and social sciences where you might be running experiments for years to look at bacteria cultures and stuff like that. And then just 2 common myths I found when I started my PhD, and I was talking with a lot of people that I don't want to, so you guys aren't just like straight away from the beginning. You might be like, well, I'm already paying for undergrad for 4 years. Like, I don't want to pay for another 4 years. Well, unlike med school or law school, most MPhDs are fully funded. So you don't pay tuition and they pay you for the work that you do. So while you're working, you can have multiple roles. You can be a research assistant. So your advisor would get funding for a project. You get to join in and work on the research, write papers, work on these projects, and you get paid for that. You can also be a teaching assistant. So the responsibilities vary depending on school and the courses, but you'd grade coursework, you'd run labs, you'd hold office hours. You'd essentially just be a teacher or a teacher assistant. And then you can also have fellowship. So it's a super flexible way of getting paid. I have 2. One is through the National Science Foundation. The program's main goal is to just fund PhD students and let us do our own thing. So I have a lot of flexibility to research whatever I want. And then I just have to do some STEM outreach stuff like this. And then I also have the Chateaubriand Fellowship, which I have a second advisor that's in France that's going to help me with my research so we can strengthen research ties between the US and France. And then the other myth is that you don't want to take more coursework. Actually, there's basically no coursework in a PhD. Master's degrees are where you do the bulk of the coursework. I only had to take 4 extra courses past my master's degree, and that's spread out over a 4-year period, so it's really, really light course load. So we spend most of our time working on research. So it's mostly just a lot of training instead. Okay, so to get to explaining cyber-physical systems, there's a little bit of a history lesson, starting with all of our industrial revolutions. So you've learned about these in history class, but we have our first, which is the steam revolution. So mechanization of all of these tasks to replace agriculture with industry. And then after that, we have these steam engines and we started working with electric power. This is where we had a lot of the physics buildup. So you might be aware of like the AC/DC ores at this point. This is where we built up all of our electric transmission through programs after the, Great Depression. And we transformed all of the transportation with the automobile and the airplane. We have big factories now. And this led to the computing and internet networking revolution. So we now have a rise in nuclear energy. In the 60s, we have all these electronics building up. So everybody now has a computer at home, a cell phone. This is where we have smartphones building up and improving. And in industry, this is where we have high-level automation to begin to take place with programmable logic controllers and robots. So the kind of automation that you see in manufacturing plants and like making cars and stuff today. Which now leads us to the 4th Industrial Revolution, which started about 5 years ago. So this is blurring those boundaries between the physical, digital, and biological worlds. So in your real life, you might notice something like a couple of years ago, you might have gotten an Alexa or Google Home. That's part of this like a CPS revolution, adding in artificial intelligence, robotics, IoT, 3D printing. It's a collective force behind many of these products that are becoming indispensable to our modern life. So how does that combine with power systems? So you might have heard of like the smart grid. So all of these IoT and cloud computing and systems integration are cybersecurity are all being part of the smart grid. We'll put different sensors and different devices on the grid to be able to monitor things. It's also becoming a way that we can design and study new complex systems, such as electrified transportation, faster and easier through new simulation and modeling techniques brought on by like machine learning, artificial intelligence, stuff like that. So yeah, we're working on electrifying everything, making everything electric, putting in a greener grid, and this is how CPS ties in with everything. Okay, so now we'll talk about some research. So I have 3 big research areas that I work in. First with traditional power systems, and then I have one with electrified aircraft, and then I do some work with vertical lift and drones. So the first is with traditional power systems. So this is what I originally really wanted to do when I was in high school, was work on committing renewables to the grid. So we want to make put all these renewables on the grid, we can't just do it automatically. It's not just flip a switch. We have to study everything. Every plant has specific physics. Every plant has both a mechanical physics portion from a like rotor spinning, which has its own inertias, but there's also electrical physics that we have to study to make sure that all these plants are interacting properly with one another. So CPS development requires well-designed models. So when we want to study all these plants coming onto the grid, we need really good models of what we already have, especially in systems where we can't build prototypes. So something like a big hydro plant. This one is in Brazil. It's 120 or 823 megavars, which means every single generator in this plant can supply power to a city of 1.5 million people. So that's like the whole Albany area. The entire plant generates 14 gigawatts, which is enough to power half of New York State's peak load for a given day. So peak load's when everybody's using power at the most for the whole day. And then, so this is a really important plant. And it's really important that when we add in new generation or want to study these plants, that we have accurate models, because if we don't, it's a mess. But we also can't make a prototype of this because there's only one river and you can't take it off the grid because a lot of people lose power. So we want to know how we can take a modeling approach that's suitable for cyber physical systems development. And we want to know how these models are developed accurate using statistical measurements that we've taken from the grid operating. So we only look at one of these generators using a device called a phasor measurement unit, which is just a little box that records the voltage, current, power coming out of the generator, and it's attached to the terminal bus of the machine. So what that means is it's at the point of the machine that's being connected directly to the grid. So we can't just attach new generation as we please. We have to study every new wind turbine, battery, solar farm as it interacts with the mechanical and electrical physics of other plants in the system. And so the reason why we looked at this specific plant is our grids are super old. They're decades old. Older plants and components change over time. This specific plant was built in the 80s. So whenever they take it offline to replace certain components, they might change and they might never get updated in the records. Things might degrade just from weather and wear and tear. So we need to know that these models are accurate. So what we did is we recreated the plant models for the generator and its respective control system using standardized models, which are used in pretty much all power system analysis tools today, and user-defined models specific to that plant. So these were models that were created by the engineers back in the 80s, and that was before any standard existed anyways. And we looked at how we can take the measurements, define the parameters that we wanted to optimize, that we would simulate the model, compare that to the measurements that we have, and then use that error to determine new parameters. And we did that using a couple different optimization methods to come up with how well the plant fit the measurements, the plant model fit the measurements. So this is cool too, because we can tie in new developments in engineering and computer science, such as machine learning, to help us compute the parameters. They actually share the same sort of optimization basis. So that's exciting. And this is kind of important too, because you can see in the figure on the bottom, looking at the reactive power, which is just, I don't know how to explain it. It's the, like, if you had like a spring in rotation or in mechanical physics, it would be, and it can store energy. It's the same sort of theory applied to, but in an electrical equivalent. So stored energy, which is the reactive power, we have this huge dip when we add in one sort of model, which I have labeled as phase D. So it's a user-defined model. And we have this huge dip, and it's super inaccurate compared to the measurements. And it turns out when we were looking at it, the engineers never considered the power electronics of the plant when they made the original model, which wasn't a big deal in the 80s. But now that we have a ton of other wind turbines and solar farms and batteries super nearby to this plant, there's all the power electronics from the grid are now interacting with the plant, and now our model's not as accurate because we never had to consider that before. And now we're seeing these errors arise. Okay, and then next I work on electrified aircraft modeling and simulation. So this is a project that's funded by NASA so that we can hit this zero emission aircraft goal by 2050. It's discussed right now. I think in the last election cycle, they were discussing it a lot and making it seem like this unattainable goal, but it's something that we're already working on. So we call it the CHEETAH, which stands for Cryogenic Hydrogen Electrified Technologies Aircraft, I think. So it's a project to explore future technologies in electrified aircraft. So instead of using conventional aircraft power systems, we're looking at cryogenically cooling the whole power system with liquid hydrogen. So there would be no emissions. What would happen is that liquid hydrogen would burn up and combine with oxygen to make water. So there's no greenhouse gases. We use hybrid electric aircraft with batteries and fuel cells. And we collaborate along with multiple engineering and science fields, from physics and material science to aerospace engineering and systems engineering, with the collective goal of making this plane to lead to a greener, more sustainable future. As a systems engineer and electrical engineer, we work on modeling multiple domains. So by domains, we consider multiple engineering fields and modeling all of their respective physics equations. So in the electrical domain, we would look at modeling all of the machines, the fuel cells, the batteries, transmission lines, and other electrical connections. In the thermal domain, we would look at modeling liquid hydrogen, cooling, the dynamics of that thermal system, and the cryogenic behaviors. And we would look at, in the mechanical domain, how the propellers impact loads and the structure of the aircraft itself. And then we have control signals coupling all of those domains together to monitor all of the states of the power system and controlling when we should use a battery instead of a fuel cell. So yeah, and then that little GIF right there is just a visualization of how we can play around with the animations in our models. And then on the right, it's a picture of what the aircraft is supposed to look like. I think it's different now though. The aerodynamics group, I think, has updated it. And then on top, we have just kind of a layout of how everything is going to be put in the aircraft itself. So we have all this liquid hydrogen storage with batteries going in each of the wings and all these fuel cells that are going to be located on the top of the plane. So instead of performing conventional and power systems analysis, what's really exciting about this project is we get to work outside of the box to determine how we're going to protect the system and identify points most vulnerable to failure, and we can transform theory into applied engineering. So specifically, we have these like cryogenic transmission lines. So they have a different electrical behavior than conventional power system transmission lines and bus bars because they're operating at 20 Kelvin. So they're super cold. They don't follow the same Ohm's law that you might have learned about in physics class. They do their own thing because aluminum gets really weird at cryogenic temperatures. We also are working with liquid hydrogen fuel cells, which is super exciting because actually all of this fuel cell development is being done at the same time as we're building up the plane. So none of these technologies actually exist yet. We're just working alongside the most novel research in that area right now. And then we also are working with superconducting machines. So these are completely new. They follow different losses and have a different structure than the conventional machines that are seen in aircraft today. And because we really only have 2 or 3 types of machines to choose from in terms of like pure physics structure, it's the same kind of machine that you would have in a lot of portions of a real power system anyways. And then my third area I work in is electrical vertical takeoff and landing, or eVTOL. And this is specifically with modeling and visualization. So for this builds off of kind of the electrified transportation aircraft project that we were working on. So we've been developing an open source library to make multi-domain drones and eVTOL models. So this means we take the same sort of modeling approach that we had to the aircraft, where we model the electrical, mechanical, and aerodynamic behaviors of the drone and the controls that dictate their behavior. All of these models are equation-based, so they reflect the pure physics of each component. And we do this because we learned that aerospace engineers usually approximate the electrical systems in eVTOL way too much. They neglect nonlinear losses, they neglect active electrical components and fuel storage behaviors, and it's pretty obvious. So on the bottom, you see this picture of the speed of a propeller in one of these drone systems over time. We apply a step, which is that blue line, it's a reference, and we consider when we add in an inductance, which is an active electrical component, which stores electrical energy over time, and we compare it to a simple DC motor that doesn't have any of that. And what we see is that because we have this DC motor with inductance, we have a little bit of a lag in speed because it has to charge up that component at the beginning of that step. So when we realize that when we increase the complexity and the detail of these models, we have a noticeable change in our models, and we need to figure out where do we hit a point that we have detailed models that can really give us a good idea of the behavior and when it's just overkill. And then the other part that we work with eVTOL modeling and visualization is we have a gyroscope testbed that allows us to collect measurements from a real drone. So in my lab, I have this testbed here that we put our drone inside of, and I have a controller that I can control, and it connects to the computer with a USB port to record the pitch, yaw, and roll of the drone over time. And we can use those measurements and the inputs from the controller to compare that to the model that we have. This allows us to use system identification, which is essentially the controls version of machine learning, to identify our models to reflect real-world behavior accurately. So we might have these ideal physics models, but the parameters might not be right. They might be one thing on the parameter sheet and different on the machine itself. And it allows, so we can make our virtual reality simulations better. In the bottom right, I have one of my undergrads. He built this little virtual reality simulation, an environment for our drone, so we can fly it around and interact with it. And so now that we have these identified models, it reflects what you would have in real life a little bit better. And it provides a foundation for estimating and calibrating larger eVTOL. So similar to how I described that big power system problem before, we can't really do that the same thing for big helicopters and big eVTOL. So something like Uber Elevate, which is a little program to look into urban air mobility. So instead of taking like a train or something across town, you can take a eVTOL, a vertical flight machine drone thing to go across town, which is becoming a viable option for bigger cities, newer cities. So something like not New York City where everything's so close together, but Los Angeles where everything's more spread apart. This might be a big viable option for public transportation instead in the coming future. So beyond the wall plug, electric power, and energy systems, this is all part of the new electrical revolution. This is where a lot of the jobs are going to be in the future, and it's an exciting area to be in. So what kind of jobs can you get in this area? So in the power systems industry, our power system, like I said, is deregulated. So everything's part of 3 different areas. So you can work in generation. There's a couple different places that you can work in generation where you could work at like a nuclear plant. The New York Power Authority owns all of our hydro plants. So like Niagara Falls is a hydro plant. We have Gilboa, which is right around the corner from here in Schoharie. And then you can work in transmission at one of the transmission operator or independent system operators. Or you can work in distribution as well at one of the places that you might receive power from, or you might get a power bill from. Plus, a lot of municipalities run their own electric generation and distribution. And then there's other industry opportunities within CPS. Boeing just signed a partnership with the company that we do a lot of our simulation programs with, which is Dassault Systems. So they are building up all of their, for the next 30 years, they're going to exclusively use these simulation tools. So they're good to learn how to use, and it really provides a promising future for CPS within industries that Boeing serves, like aircraft. So Boeing and similar companies will benefit from this type of research and the teaching that involves the development of these skills. And then other companies that you might have heard of is Tesla, that also is looking into using, getting engineers that know how to use a lot of the programming tools that I use in my research. One of these is called Dymola, which is where we develop a lot of the models for the electrified aircraft in. So that's another promising area to look into. So in conclusion, automation will continue to improve human life. There's really no way of getting out of it at this point. We're going to be stuck with cyber-physical technology for basically forever because it's becoming indispensable. So in the future, we're going to require many areas to collaborate between programmers, engineers, etc. The future of energy will also require increased efforts in automation with the challenges brought on by renewable energy resources. So we'll have this tighter integration of physical systems, cyber systems, and people. And training for cyber physical engineers is absolutely essential. So this is a really cool area to get into in the future if you're interested in it. So yeah, that's all I've got if anybody has questions.
So folks, with your questions, you could either type them in the chat or you could raise your hand. You can unmute yourself. Okay, Tyler has a question.
First off, that was all very interesting, so thank you very much. I have one question actually specifically about, I guess, your undergrad and like grad school. How exactly did you do undergrad and grad, I guess, at the same time? Because you said you graduated like the same year, right?
I graduated in the same semester. So a lot of schools have these things, they're 5-year programs that you can, after your, a lot of them let me start over. So yeah, there's these things called 5-year programs where you do your bachelor's for 4 years and you tack on a 5th year for your master's. And you will do your first 2 or 3 years, and then you have the opportunity to apply. A lot of the time, the application process is a lot easier than if you chose to apply to grad school the traditional way, since the school already knows your grades and they already let you in as an undergrad, and their standards are pretty much the same for undergrad and graduate. And then your financial aid, for the most part, at least at RPI, will carry over to that 5th year to do your master's. So it's a really great opportunity if you have a really good financial aid package or you got a really good merit scholarship. So in my case, it was really good. And I also did it, so I took a bunch of AP courses at Colony, and I decided I didn't want to take them over when I got to college. So I came into college with 30 credits, which covers about a whole year. So after my sophomore year, I applied to the master's program. They let me in, and then I just took the classes in with the rest of my undergrad classes and just finished them at the same time. I recommend doing it if you can do it, because it just makes life easier. You don't have to wait.
Yeah. There must be other questions from behind your yearbook photos on the screen. It's hard, isn't it, Megan? It's hard to talk to people when you can't see their faces. These photos.
No, we don't ever turn on cameras.
Any questions? Come on, guys. You got to have questions. I see Tahira has her hand raised.
So, like, the cryogenic part of the airplanes is, like, really interesting how you can, like, not have, like, emissions and, like, kind of just, like, produce water. And I was just wondering if you guys use, like, the concept of cryogenics with, like, any other stuff with, like, power and stuff like that, like, to, like, reduce emissions, because I think it's, like, really useful.
So yeah, so in traditional power systems, no, since everything's just out and about and can be cooled by the regular air. I don't know, because this is the only project I work in with this specific thing. I know in with the group that does the cryogenic machines, they've used it, I think, for cars as well, and looking into using other sorts of fuel cells that operate at cryogenic temperatures as well to cool. So yeah.
All right, thank you.
Megan, maybe I can ask you a question because
Okay.
I'm curious. I know you said like take all the regular courses and so forth. Can you give them some advice, being high school students, what classes they really should consider taking if they want to move into a STEM field? Because a lot of the courses are electives, and so maybe you can give them some advice as to what you think is necessary.
I think for me, the most helpful ones to get out of was taking Calc BC was the best because it gets you out of Calculus 1 and 2 when you get to college. Taking AP Physics was also good just to get the course out of the way, and I could just take the E&M course, but also just provides a good foundation. And then do we still have the engineering electives?
Yes, we do.
Okay, yeah, all of those engineering electives are really helpful. I was most interested in electrical engineering, but I think they all provide a really good foundation, whether you're interested. I think they cover pretty much every engineering field from, I know we have a biomedical course, civil, electrical, POE is basically mechanical engineering. So all of those are a really good foundation, and it gives you the opportunity to sort of explore and figure out what you don't like ahead of time, so you don't have to waste time in college or have a crisis when you're already away from home. Like you can just try everything at low risk in college or in high school already. So those courses I think were the most beneficial for me.
And I have a little bit of a follow-up to that. You chose to go into engineering instead of into science, which involves a lot of the same coursework. Can you explain why you chose engineering versus science?
Yeah, so engineering is more like applied and problem solving. So I like the work engineers do a lot better. Yeah, I wanted to go into power systems too, and you can really only go into power systems if you're an engineer. Engineering is also just more so applied science. So electrical engineering actually shares a lot with electricity and magnetism-based physics. So instead of working in the theoretical, I hate the theoretical side of everything. So instead of working in the theoretical side of everything, you get to see everything applied. All of the same foundation is just now applied to specific cases, like in machines or transmission lines. So that's the main thing. And I think a lot of other engineering areas are the same thing, where they're just applied sciences as well. So.
All right, thank you. Now I know there are many ninth graders in our Google Meet tonight. So can you think back, Megan, when did you take that digital course? Was that 10th grade?
It was 10th grade. Oh yeah. If anybody wants to hear my embarrassing story of how I got into engineering, I in 8th grade decided that I wanted to be with the rest of my friends. So I was going to sign up for art. And I got to school on like the that like introductory day. And I hated art. I like went home and I like complained to my mom, and my mom like went to the guidance counselor. They got me out of it. I like had to be on a wait list to get into CAD and had to wait for somebody else to drop it. It was a mess. So after that, I learned to just do whatever I wanted instead of following what my friends did. And then and then after that, I don't even know how I ended up in digital electronics. It was just like the course sign up day, and like I was like, I don't know what class to take, and they were like, well, just take digital electronics, and I was like, okay. So then I ended up taking it. I had no idea what it would entail until like the first day of school. So yeah, that was my sophomore year that I took that though.
Okay, because I know like we're going to be doing course selections in about a month. So I'm thinking ahead to, you know, if students think they might be interested in pursuing a career path or educational pathway similar to yours, that would be a good time to, you know, obviously you want to talk to your guidance counselor soon or talk to the teachers in the tech department. You can email them as well in terms of those courses to find out what options are available to you.
I wish I knew ahead of time. I feel like I just went wherever I was told. So.
Well, and I have a feeling a lot of our students do that too. They follow the pathway that the teachers are kind of telling you, you should just do this. Just do this.
Yeah, somebody just said yes in the chat.
Yeah. So you have to kind of decide, what do you like? But, you know, you should take a little bit of advice from your, you know, teachers and people who are in the field in terms of what's important to do for that. You know, don't just go along with the crowd. Now, you know, I'm going to get some angry emails from parents later saying, you told my child not to. No, that's not what I'm saying. What I'm saying is that you have to find that balance between what you need to take and also what is good for you to take, so that way you have options in terms of, you know, also exploring this. Your high school years are about exploring your future, not just fulfill. You do have to fulfill your graduation requirements, but you should also think about your future. And definitely, I would say as a physics teacher, I'm going to give the plug to take, if you're thinking you want to do something in science, math, or engineering, that you should take as many math, science, technology courses as you can.
Yeah, I didn't take that many science courses, so.
Yeah, well, you did. You took your AP. You were with me for AP.
Other people took loads, and they were like, they never had lunch because they always have labs. I don't like labs, so.
Ellen.
I'm not particularly good at science, so.
Don't let her tell you that. She was a great AP physics student.
I have a question. I was just wondering, did you take any other science classes like AP Bio or AP Chem?
No, not at all. Part of the reason, I took physics. I didn't have time to take anything else because I took all the Project Lethal Way courses instead. But I think that was just a good replacement instead of the AP courses for what I wanted to do as an engineer. I think it prepares you better to be an engineer if you want to study engineering, to take those courses instead, since when you get to college, you'll have to take either chemistry or bio anyways. So it's better to like know in advance that you like it instead. That's just my opinion.
I would agree. And you made a good college choice, Meaghan.
I know.
I'm a little biased myself, having gone there. Good choice.
It's a good place to be.
And it's a nice place to visit too. So once their campus reopens after the COVID shutdown stuff, I mean, you can always go walk. I believe they're not going to stop you from walking around on the campus and looking at buildings.
Nobody's there. Every time I went the past couple of months, it's been pretty much empty. So you can just walk around. You can't get into any buildings because they changed it so you could scan in so they could contact trace, but you can't go anywhere.
Tyler,
Yeah.
I see a question. Another question.
So that actually that actually makes me wonder. So how exactly are you doing like a PhD, like all the stuff you're naming and all the stuff like you talked about? How are you able to do that right now? Like how do you do that during the pandemic? Because for us, it's like, okay, well, we have class and it's like a virtual lab, but like, how do you do actual research that's going to, you know, affect hundreds of thousands of people, you know, in the coming years, like online, I guess?
Honestly, I had the easiest transition of anybody, actually. All of our research, because I do modeling and simulation, with the exception of like my test beds, which are all I gave to all of my undergrad researchers. So because they all lived local, so they all got driven to their houses. I can't work on any of that right now, but all the modeling and simulation stuff I can just do on my computer, or I have another machine that I can remote into. And then with the projects that I'm working on, the Cheetah project is with I think 11 other universities. So we've been meeting remote beforehand anyways, and I've been used to meeting remote with them. So it was no change. Instead of just going down to my advisor's office to go sit in the meetings, I had to just log in myself. And then my research with my other advisor in France, we've obviously been meeting remote before this, and we will keep meeting remote. So actually there was no change. But I'm just really lucky because everything is already on the computer. I know a lot of other research labs have specifically switched in the last 6 months to focus more on modeling and simulation based and computer based research. One of the conferences I submitted a paper to, we submitted it. There's a modeling and simulation session, and that was like, there was like 50 papers submitted to that session and like 10 to every other session, because all anybody's been doing for the past couple of months is modeling and simulation because there's nothing else to do. You can't do anything else. So I got lucky though. That's just the nature of the work. I do know the power grid, everybody's been working at home because my boyfriend works at the independent system operator of New England. Everybody's been working at home, and then at the worst point of the pandemic, the actual operators themselves were, at least for New York, living in a trailer in the parking lot. So they work in East Greenbush. If you drive on 90, there's a building with no markings on it. That's the ISO. They were working out of a trailer so that they could stay isolated. So your whole grid has been run remotely at home, with the exception of people living in a trailer.
That takes dedication, Meaghan.
I know. They were trying to like bully, I guess they were having meetings and they were trying to get everybody else online. They were like, y'all, it's a great idea to have they were like, we're not going to make them live in a trailer. They do one shift at the regular center now, and then they do one at the backup control center for New England. So they have time to clean.
Yeah.
So yeah, it's dedication.
Well, Meaghan, I have to say this was really awesome. I loved seeing you present and teach me things I don't see. This is what happens, guys. You're going to go off to college. I want you to remember all of your former teachers so you can come back and tell us about these amazing things you're doing. Just like Meaghan is coming back years, not that many years later, but enough years where I've kind of seen you. I mean, you know, a little bit. I've heard a lot about what's been going on with you, but not actually had a chance to chat and learn in depth about what you've been doing. So it makes me incredibly proud. Thank you so much for sharing back with our colony community. I believe they all appreciate it. Otherwise they wouldn't have come. I don't think they would have come tonight.
This is a huge group. It was more than I was expecting.
Yeah, no, this was fantastic. I'm thrilled. That's nice that we're getting our thank yous in there. So what I'd like to do, those of you who are new to STEM Club who joined us for this meeting tonight, you'll see in our Google Classroom under the classwork tab, there's a couple of new additions in there. I just want to point out to you. We'd like you to continue joining us, and you'll see under the classwork tab that there is a STEM Club registration form. If you could please complete that, I would very much appreciate it so we can try to tailor our activities towards your, yes, thank you. If you've already registered, you're all set. It's just for those of you who are new that did not register last week at our first meeting. And the other thing you'll see is that copies of Meaghan's slides have all been posted. So for every meeting when we have a guest speaker, if they're willing to share them with us, I will post them there so you can see them. You see her email address is on her title slide. So you should feel free to reach out to her if you have any questions in the future. I will also post a link to this meeting's video recording. So if you ever have questions and want to go back and review it, you can. Okay. Does anyone else have other questions before we adjourn for tonight? All right, I'll just let you all know that we will not have another meeting next week, since next week we're officially on vacation next Thursday night. Thursday's the beginning of our vacation, and we will resume our meeting sometime in January. I don't know an exact date yet. So just keep your eyes peeled in our Google Classroom where we'll announce it. I know Mrs. Thomas at the high school has been very good about posting it, and some of your folks may know as well from the Facebook page for the PTA. So we've been posting them there too. All right. Meaghan, I really appreciate it. Again, thank you so much. Oh, it's been a pleasure. You got to say hi to everybody at home for me. Say hi to Mom and Dad.